Okay, so in this lesson, we are going to be introducing the derivative, which is pretty exciting. So we're going to start off with some review. The average rate of change is something you should have learned about. So the average rate of change of a function f of x over the interval a to b is given by doing f of b minus f of a over b minus a. And what that average rate of change tells us is it is the slope of the line through the points at the endpoints of the interval. So it's the slope of the line through a comma f of a and b comma f of b. Okay, so I would like for you guys to practice finding the average rate of change of the following two functions. These are two different functions over the interval -1 to 3, so you should pause the video and attempt to do them and then start it back up when you're ready. Okay, so I'm going to go over them. So average rate of change, sometimes I abbreviate as AROC, A-R-O-C, will be equal to f of 3 minus f of, in this case, -1 over 3 minus -1. And so off to the side, I'll find f of 3 and f of -1. So here we have, 2 times 3 is 6, 6 plus 3 is 9, square root of 9 is 3, and then 2 times -1 plus 3 is going to be 1. So here we have 3 minus 1 over 3 plus 1, which simplifies to 2 over 4, or 1/2. So that's our average rate of change for that function. For the other function, you're given a graph instead of an equation. So I'll zoom in a little bit. And remember, it's still the same thing. So the average rate of change here is still going to be f of 3 minus f of -1 over 3 minus -1. But now we can find f of 3 and f of -1 from the graph. So f of 3 is 8, f of -1 is 0 over 4, and that will simplify to 2. So what that 2 represents is it is the slope of this line. Okay. Now, a big question in calculus is what is the instantaneous rate of change? So instead of caring what is happening, what's the rate of change over this interval of time, we want to know what is the rate of change at this moment, like right now, what's the rate of change? So the instantaneous rate of change of a function at a point AB is defined as the slope of the tangent line at the point AB. And so the tangent line is going to be a very big deal in this class. So the tangent line is just it's a line that touches your function at one point, versus the line that's over here, this line over here. I guess I should maybe use a different color. This line here is called a secant line. Okay, a tangent line would be, you don't have to draw this, but if I wanted to draw the tangent line like at this point, it would be like that. Like it touches it at that point rather than through two different points. Okay, ignoring that for now. It is not always possible to find the instantaneous rate of change if you're given a table or a graph. So you're going to learn in future lessons how to do it from an equation. But if you're given a table or a graph, it's not always possible. And so sometimes you're going to have to approximate it using the average rate of change. So you can approximate the instantaneous rate of change using the average rate of change. And we're going to practice that here. We have a function f of x. We have a table for it. It's continuous and differentiable. We'll talk about that later, what that means, for all x with selected values given below. Estimate the instantaneous rate of change for f of x at x equals 4. So the first thing you want to do is you want to find like the closest points around 4 that are given in the table. X values, right? It's an x value 4. So x equals 4 would be in here. It would be in between 3 and 7. And so this is the area that we are going to use. So here I'm going to say that instantaneous rate of change, IROC, at x equals 4 is approximated using average rate of change. So f of 7 minus f of 3 over 7 minus 3. This doesn't mean it's a good approximation, but it's an approximation. So f of 7 from the table is 5, and f of 3 is 1. And then that is 4 over 4, which simplifies to 1. So that is our approximation for the instantaneous rate of change. Okay, now, what the heck is a derivative? So we have several bullet points here explaining a bit about what a derivative is. So a derivative, f prime of x, that's how we read that, is a function that tells you the instantaneous rate of change of the function f of x with respect to the change in x. Okay, so the derivative is telling you the instantaneous rate of change. We're going to spend a lot of time studying derivatives, so you will improve at it, but understanding the meaning of the derivative is really an essential part of this class. When you find the derivative function, it is also a function of x, meaning the inputs would still be x, so it's still a function of x. And finally, the derivative gives the slope of the tangent line. Okay, remember from up above, up here, the instantaneous rate of change is the slope of the tangent line. So we have like different words that all kind of mean the same thing. Derivative, instantaneous rate of change, slope of the tangent line. Those all are sort of the same thing. So derivative gives the slope of the tangent line at a given point. We have several notations for derivatives. So you want to get familiar with all of them. So one of them is the Leibniz notation, and in that notation it looks something like this. So d dx, that's how we say that, d dx. D dx of f of x, that means derivative of f of x. Sometimes it's not f of x, sometimes we have d dx of y. Or you could also see that written as dy dx. So these all sort of mean the same thing. So that's the Leibniz notation. Okay, then we have the Lagrange. Lagrange is usually what people say. Notation. And that one for f of x would look like this, f prime of x. Okay, so it's less writing. A lot of students like this one better. Or if it's a y, we can just say y prime. Or sometimes we just say f prime and we don't put the of x. So how you read that little thing is prime. And it's not an exponent, okay? It's not an exponent. From the context, you should be able to tell what it is. So explain the meaning of f prime of 3 equals -7. So one way we can interpret this is the slope of the tangent line to the function f of x at x equals 3, right? So the input is 3, is -7. -7 is the slope of the tangent line. We can also, instead of slope, we can say instantaneous rate of change. So instantaneous rate of change and slope of the tangent line are the same thing. The instantaneous rate of change of f of x at x equals 3 is -7. Okay, so both of these are good explanations for what that f prime of 3 equals -7 means. So now we're going to move into actually writing the equation of a tangent line. So here we go. I'm going to keep repeating this part too so that we really drill it in your head here. Reminder, graphically, a derivative tells us the slope of the tangent line to a function at a given point. Okay, to write the equation of the tangent line, we always need two things. This is just like what you would need to write the equation of a line. To write the equation of any line, you need to know a point and the slope. So to write the equation of a tangent line, same thing. You need a point and you need a slope. So we're going to write a little formula here, but really you can just use your prior knowledge of writing equations of lines. We tend in calculus to use the point slope form rather than the slope intercept form. So writing the equation of a tangent line of f of x at x equals c. So the point, right, the c value is the x value, and then your y value would be f of c. Because our function is f, right? To find the y value, you have to plug your c into your function f. So that's your point. The slope is the derivative. It's the derivative of the function f at the point c. So we can represent that using the derivative notation, f prime of c. So that means derivative of f at c. And here, off to the side, I'm going to write the point slope form. Y minus y1 equals m times x minus x1. That's the point slope form. And I'm just going to write that same thing, but instead of using x, y, and m, here, I'll maybe label. This is the x, this is the y, and the slope is the m. So our equation would be y minus, instead of y1, oh sorry, these would really be x1 and y1. Okay, y minus f of c is equal to, instead of m for slope, I'm going to put f prime of c times x minus c. So that's going to be the equation of the tangent line. Let's give it a go. A function f of x is continuous and differentiable for all values of x. It is known that f of 4 equals 7. Okay, so that is a point. That's a given point. X is 4, y is 7, and f prime of 4 equals 2. So that is the slope. The slope is 2. Write an equation of the line tangent to f of x at x equals 4. So our point is 4, 7. Our slope is 2. And so you're just going to use the point slope form to write your equation. Y minus 7 equals slope is 2 times the quantity x minus 4. You can leave it like that. You don't have to then get it into the form y equals mx plus b. Unless it specifies, like, write it in that form. You can just leave it like this. It said write an equation, we wrote the equation. Alternatively, if you prefer to do it the other way, you can. But a lot of times in this class, this form will be most useful. Okay, now, hopefully you're feeling pretty good up until now. Now we're going to use the limit definition to find the derivative of a function, which gets a little messy. This can get a little messy, and some of you may already know how to find the derivative more quickly than what I'm about to show you, and that's great. But for today, you have to do it the long way, okay? In today's homework, you have to do it the long way. In the next class, we will learn how to do it in a faster, more efficient way. But for now, it's important that we practice it this way. So please be patient. Okay, so the definition of the derivative, this is the the actual definition of the derivative, is the derivative f prime of x is equal to the limit as h approaches 0 of that function there. F of x plus h minus f of x all over h. So if we want to find the derivative of f of x equals x squared plus 2, I am going to chunk this. I'm going to color code a little bit. I'm going to highlight that part in green, and I will do this in purple. Okay, so I'm going to start off by finding f of x plus h. So f of x plus h. Okay, so that's just plugging x plus h into my function that's given. And then I'm going to multiply that out. So I would get x squared plus 2xh plus h squared plus 2. Okay, so this is my green part. So this is this. Okay, we already know what f of x is. That's given. So now we are going to write f prime of x is equal to the limit as h approaches 0 of f of x plus h. So that's that whole thing we just wrote. X squared plus 2xh plus h squared plus 2 minus f of x, which I'm going to use parentheses, is x squared plus 2. Okay, so let me go back to my color coding. This is my green, and including the 2, this is my purple, and then this whole thing is divided by h. Okay, and now you're going to hopefully simplify. So here I have an x squared minus an x squared, and then I have a 2 minus a 2. So we're doing a little bit of simplifying. So all that's left is this here, and that I can factor out an h. So now I have limit as h approaches 0. I'm going to factor out an h. I'm left with 2x plus h over h. These h's cancel, and now I can just plug in 0. And be careful here. Are we plugging in 0 to x or h? We're plugging it into h because we're talking about h approaching 0. And so we're just going to end up with 2x. So we just found that f prime of x, the derivative, is 2x. So the original function was x squared plus 2. The derivative function is 2x. Notice it's still a function, okay? So we got the derivative, and it's still a function. It's still a function of x. Now, let's write the equation of the tangent line to the graph at a point. So in order to write the equation of the tangent line, you have to be given a point. You're always doing that at a point. So here, we're going to follow. The point is 1, 3. So our point is 1, 3. And our slope, we have to now plug in the x value to the derivative. So this one we're not given. Earlier we were given what the slope was. Now we're finding it. So the slope would be f prime of 1. You're plugging in the x value to the derivative. The derivative function was 2x. So we're plugging 1 into 2x. So we get 2 times 1, which is 2. So we have our point, we have our slope. We can write our line. Y minus 3 equals 2 times the quantity x minus 1. Okay, if you want to, you could rearrange that. Now let's sketch it, okay? So over here, I'm going to sketch it. So at the point 1, 3, the tangent line would look like, now it's really hard to draw these by hand, but it would look something like that. Okay. So that's the tangent tangent line at x equals 1. All right. Now, this part, it can be a little bit tricky. So these limits below represent f prime of c for a function f and a number c. Find f and c. Okay, so here, let's write the limit definition again up top so you can see it. So f prime of x equals limit as h approaches 0 of f of x plus h minus f of x all over h. Okay, so here, f prime of x gives out a function, right? That's what we said earlier. When we had f of x was x squared plus 2, we found its derivative. The derivative was 2x. It was still a function. What's going on here, I think that tends to confuse students, is these represent f prime of c for a function f and a number c. So this one, a number is being plugged into the function. So let's just write this out up here. I'm just going to write it with a c instead of an x. F prime of c. So it's going to look like limit as h approaches 0. And instead of f of x plus h, it has a number c plugged in minus f of c. So that would be the function f evaluated at some value c all over h. Okay, so you're trying to figure out basically what is the function f and then what is the value c. So the first thing you want to do is see, like, what does the function look like? And I encourage you to pause this and try to figure it out. But if you're really stuck, maybe watch me do the first one and then you try one. So for this first one, I'm going to zoom in. I'm looking at what the function is and then what this is. So to me, it looks like that function, f of x, is the square root of x, right? And then something got plugged into it. What got plugged into square root of x? The thing that got plugged into there was 9 plus h. So 9 is the c value because it's f of c plus h. Then you want to make sure it works. You want to make sure, is this f of c? That should be f of c. So if we're saying that c is 9 and f of x is square root of x, square root of 9 does equal 3. Okay, so here the function is square root of x and c is 9. Okay, now on this one, looks maybe a little bit scarier, but again, I see that I have this is my f of x plus h, or in this case, c plus h, and then this should be my f of c. Okay, so it looks to me like that looks like 2 plus and then something cubed, right? 2 plus, and then that's the c plus h in there. So that would mean that the function is 2 plus x cubed. And we're going to make sure it's right. It seems like the c value is -3, so you would make sure that if you plug in -3 to the function, you should get -25. So let's see. If our function is 2 plus x cubed, now we're going to do 2 plus -3 cubed. That's 2 plus -27, which is -25. Okay, so the function is 2 plus x cubed, and the c value is -3. So that can be really, like, for some students, that can be really confusing because you're kind of thinking in a different way, thinking backwards. But it's just a good exercise to try. By the way, I'm recording this during the 7th period, and the The bell's going to ring because I'm not going to finish this, so excuse the bell. Sorry if it's super loud. Okay, a little bit more. We have here another form of the derivative. So this is, I don't know, they call it the alternate form of the derivative. It's just another limit definition of the derivative. The difference is that this is at a point. So at a point C. So this is just another limit definition of the derivative. Okay, sometimes it's more useful. You should be comfortable with both definitions. And it takes some practice. Okay, find the derivative of f of x equals the absolute value of x minus 2 when x equals 2. So this is really asking us to find f prime of 2. And in this case, 2 is your c. Okay, so we're going to use this limit definition of the derivative to do this one. So f prime of 2 is going to be equal to limit as x approaches 2, because x is approaching c, of f of x minus f of c, so in this case that's f of 2, over x minus c, and again c is 2. Okay, now let's fill in, so limit as x approaches 2, f of x is the absolute value of x minus 2, minus, now let's find f of 2. If we plug in 2, absolute value of 2 minus 2 is 0. Okay, so this is, now if we tried direct substitution, if you just plugged in 2, you would end up with the indeterminate form 0 over 0. So this is one of those ones we talked about in a past class, absolute value of x over x, and one of the tricks was to write it as a piecewise function. So I'm going to do that over here. Absolute value of x minus 2 you can write as a piecewise function. Similar to what we did in a past class, it's going to be negative quantity x minus 2 if x is less than 2, and then just x minus 2 if x is greater than 2. And you want to put the or equals to on either one. It doesn't matter which one. So that's the absolute value function. So here, we're going to use left and right limits and then see if they match. So we're going to split this up into left and right. So I'm going to do limit as x approaches 2 from the left. Because we're approaching 2 from the left, I'm going to use the top piece of my piecewise function. And then the x minus 2 and the x minus 2 cancel, and I'm left with negative 1. So that's the left limit. Now let's do the right limit. Right limit, you can just drop the absolute value because you're using the bottom piece of that piecewise function. And those also just cancel, and you're just left with 1. So the left and right limits don't match, therefore f prime of 2 does not exist. Right? Because if the left and right limits don't match, that means that the original one that we were working with here doesn't exist, and that is the limit definition of the derivative. So f prime of 2 dne, since limit as x approaches 2 of f of x minus f of 2 over x minus 2 dne. Okay, and so graphically, let's discuss this real quick. That means that at this point 2, so this is the graph of our function, the function is not differentiable. And really the reason is that, we can talk more about this another day, but At any point along this line, you could draw the graph of your tangent line, right? It would just be that line. And same thing over here, you could draw your tangent line. But here, what's happening as you're getting closer and closer is that they don't agree. It's like, how do you draw the tangent line here? How would you draw the slope at that point? So it's not differentiable when it's pointy like that. I'm sorry, this is getting kind of long, but this is just a good foundation for the rest of the year. Now I wanted to do a visual representation of the limit definitions of the derivative, just to really like try to show you guys like why they work. So the first one was limit as h approaches 0 of f of x plus h minus f of x all over h. So here's what we're going to do. I'm going to put down here just a point x, and then we're going to call this x plus h. Okay, so this distance here is h. Now, f of x plus h would be right here, right? This point here would be the x value x plus h, and the y value f of x plus h. And this point here, which I'm going to write up a little bit higher, is the point x, comma, f of x. Okay, so f of x plus h minus f of x over h would just be, that's the average rate of change. That would be the slope of this line. It's the change in y, the change in the y values, f of x plus h minus f of x, over the change in the x values. X plus h minus x is just h. So this is the average rate of change. It's the slope of that line. Now, if you think about, let's maybe write that out. So f of x plus h minus f of x over x plus h minus x. This is the average rate of change. And then we're going to cancel those x's out. And you're just left with the h down there. Okay. Now, if now you want to find the limit of that as h is approaching 0. So think about as h is approaching 0. As this is getting smaller and smaller, that means there are some good visuals of this if you look them up online, but that would mean that this point is getting closer and closer, right? The gap between x and x plus h is tending towards 0. So they're getting virtually like right on top of each other. The difference between the two is tending towards 0, and that would give you, if there was no gap, that would just leave you with this point and the slope of the line there, which is the tangent line. Okay, so as that gap, as h is tending towards 0, the point, the x plus h, f of x plus h point is getting closer and closer to the other point, and then you're left with the instantaneous rate of change. So the limit as h approaches 0 of that thing that we just wrote is the instantaneous rate of change. Okay, just for time's sake, maybe you can try this one as an exercise. So this one, you're going to do the second definition, which is the limit as x approaches c of f of x minus f of c over x minus c. This one, you're going to treat this as like a point c and this as x, and then just kind of, it's the same process. So you try that one out. I'll post it on the completed notes so that you can look at it. Okay, which brings us to the end. This a page maybe doesn't look significant, but this is going to be incredibly important. So what the heck does differentiable mean? You've seen that kind of throughout the notes. It's mentioned a function is differentiable. So a function is called differentiable if it has a derivative everywhere in its domain. Okay, and in order to have a derivative everywhere in its domain, it must be continuous. We already know continuity, what that means, and smooth. Smooth basically means like not pointy. It should curve and it should never be pointy. So functions on closed intervals must have one-sided derivatives defined at the endpoints. You don't need to worry too much about that right now. So derivatives fail to exist in these situations. Corners, which you can see there, like the absolute value function, cusps, vertical tangent lines, and discontinuities. So a derivative failing to exist is different than a limit failing to exist. These are two different things, so try to not get those mixed up. And this is the part that is also super important. If f is differentiable at a point, then it is continuous. If a function is differentiable at a point, then it is also continuous. So I want you to write really big down here. Differentiability implies continuity. If you're ever told this function is differentiable, then you can assume that it is continuous, but the converse is not true. So if a function is differentiable, then it is continuous. Therefore, if it's not continuous, you know that it's not differentiable. However, continuity does not imply differentiability. It can be continuous, but not differentiable, like at a cusp or a corner, right? So like on the absolute value function, this function is continuous, but not differentiable everywhere. It is differentiable in a lot of places, but not at that pointy part. Okay, so I know that was a lot. This is like a really big lesson, but also a really important one. So just bear with me. A lot of this is going to continue to come up and you will get better at it. Okay, good luck on the assignment. You have it down below for you.